We've talked so far about capturing the sun's abundant energy, turning it into electricity. We've also talked separately about storing that energy that's been turned into electricity. Well, do we have to think of these things as separate, as disjoint? Is there some precedent, perhaps, in nature for this? Well, of course, there's a very familiar precedent. What do trees do? What do plants do? They take energy from the sun, and they convert that energy into a stored form. They convert it into a fuel. You may not necessarily think of the food that you eat as being a fuel, but that's exactly what it is. So there's a dream, and a dream that's made vast progress in recent years, a lot of it relying on nanomaterials and nanotechnology, that involves mimicking all of the good qualities of photosynthesis. It's called artificial photosynthesis, and the idea is that we could use sunlight to directly generate fuel, such as direct production of hydrogen. So let's start off by taking a bit of a look at photosynthesis and how that works. We'll find that nature is, as we already know from this course, very much a nanotechnologist in the way it engineers materials to a particular purpose. Photosynthesis is the conversion of carbon dioxide taken out of the air into organic carbons. That's from the carbon dioxide that the photosynthetic reaction takes the carbon as a source. And with this, it produces sugars, which, as I said, are fuels. Now, we know that it occurs in plants. It also occurs in algae and lots of different species of bacteria. There's a nice word to describe these organisms that are capable of harvesting energy and creating their own food. We call them photoautotrophs. And this references the fact that they're self-sufficient. They're really capable of building their own nutrition rather than relying on others, as we humans do, to be our sources of food. If you like, they eat photons. And so, attractively, they consume carbon dioxide and water, and they release oxygen as their waste product. Sounds very clean as waste products go. Now, we talked earlier when we were talking about solar energy of how we could readily, in terms of the amount of solar energy that's available reaching the Earth, we could readily meet the world's energy needs 10,000 times over using solar energy, using solar electricity. Well, of course, plants and algae and bacteria that perform photosynthesis are already harvesting a huge amount of solar energy. In fact, if you look across the globe, around the globe, at all of the energy harvesting activity that's happening right now, there's about 100 terawatts. This translates into about 6 times more power than human civilization is consuming. So it just reinforces the idea that there is this vast source of power, and that the key is to find cost-effective ways of harvesting it. What's a cost-effective way? Well, the brilliance of plants is unlike these solar cells that we've been talking about earlier in the course, where we have to go engineer them, we have to invest energy, we have to purify materials to make them. The plants, of course, are ultimately using the energy from the sun to build themselves. And so they're self-sustaining, they're self-constructed, they're self-assembled. And so it's wonderful to dream in the context of this notion of artificial photosynthesis, ultimately of the photosynthetic apparatus that we engineer to build our fuels, having it build itself, rather than having consciously to engineer it ourselves. And we'll finish this lecture with some progress in that direction as well. But back into what happens at the heart of the organism during the photosynthetic process. In fact, the chlorophylls that are used in the absorption of light and that capture that energy from photons, turn them into energetic electrons, which are then available to participate in reactions. They're actually part of a membrane, tightly folded into these cylindrical sheets called thylakoids. They're bunched up together. And these structures are used to fill up the interior of a cell, ultimately giving the membrane a very large surface area. I want to emphasize this because it's so resonant with many of the themes of the course so far, where we are trying to maximize surface area by folding, by creating richly textured surfaces on the nanoscale. Well, we may think we're smart, but bacteria had already thought of this. This kind of strategy is already widely used throughout nature. So when light absorption occurs in these proteins, they're called photosynthetic reaction centers. And here the photosynthesis is really at work. The light is coming in, and then reactions are occurring relating to chemical synthesis. We're actually building fuels within leaves. It's right at the chlorophyll that is the heart of this, and it's the chlorophyll that gives leaves their green color. I mentioned when we were talking earlier about solar energy that the sun finds its peak right in the visible spectrum. And the green is right in the center of the visible wavelength spectrum. And so this is a very abundant source of energy coming from the sun. That aligns nicely with the fact that the energy required to drive forward these photosynthetic reactions is less than what we can get out of the energies available in the photons coming from the sun. So we have sufficient energy within each photon, within each of these quantum particles, to perform the chemical synthesis that we need to do to turn carbon dioxide into organic compounds. So it's this chlorophyll that's giving these plants their green tinge. That's this pigment, really. It's like a dye, something that's used to dye clothes. It's very persistent, hence grass stains in pants. And these pigments are embedded in plants and algae in what we call antenna proteins. And this is where some fascinating physics occurs. The process that's occurring inside these reaction centers is known as energy transfer. Now, when we think of energy transfer occurring using light, what we would often think of is light being emitted and then being absorbed somewhere else. So, for example, if I wanted to convey some energy from here across the room, I could construct a laser here, and I could drive it with electrical energy, convert that into a beam, try to focus that beam onto, say, a photovoltaic cell across the room. That would be energy transfer within the optical domain. But inside the antenna proteins within the reaction centers that make up plants, we have what we call a virtual photon emission event. We have the capability for energy to funnel itself downhill, to roll downhill through a series of centers without actually ever going from being an excited electron to being a photon to being another excited electron. But with this downward cascade, we're able to direct the flow of energy. When we spoke in the lecture about nanomotifs, about nanoparticles that were being engineered to have different sizes and that therefore had different energy levels, and where we were able to concentrate all of the energy from an outer ring of nanoparticles onto a central receptor, what we're really doing there is we're being inspired by the photosynthetic reaction center that occurs inside plants within the photosynthetic reaction apparatus, as it's called. What kinds of efficiencies do plants have in their energy conversion? Well, this too raises an interesting point. It turns out that the range is typically 3 to 6%. How does that compare to the best solar cells that we could make? That's actually considerably worse than the best solar cells. The best solar cells, the records are in the 40% solar conversion efficiency range, and there are commercial solar cells that are a little bit under 20%. And so this incredibly successful predominant source of energy harvesting, which is the photosynthetic approach rather than our artificial solar electric approach, the one that's less efficient, the one that's 3 to 6%, the photosynthetic one, is the one that really has caught on and dominates our global use of energy. Why is that? Well, think back to the solar lecture where we were thinking about both the cost of making the solar cells and panels, but we were also thinking about what we call the balance of systems costs. We were thinking about installing solar panels, the maintenance of those solar panels. Well, the brilliance of the way in which life and biology manage photosynthesis is in part this self-assembling process that we described. There's no balance of system costs. In fact, we enjoy having plants and trees around. It's not a cost, it's a benefit to have photosynthesis at work. The production of oxygen is a benefit for us. And so this aspect wherein the self-assembly of these devices, as an engineer might think of them, these trees and plants, is one of their many very attractive features. And it's a reason why perfection in terms of energy conversion isn't required. After all, there's so much more solar energy than we need. We don't need to be absolute perfectionists in the efficiency in which we convert a certain photon having a certain energy into a stored chemical such as a sugar inside a plant. And so our analogy in building a device that will mimic photosynthesis looks kind of like this. We also will have photons coming in. Here we imagine having a large area device available to receive a lot of sun. There will be an input into the reaction, and in this case it will be water. And the output of the reaction will be to split that water into two essentially innocuous things. One of them oxygen, a byproduct of the reaction, just as a byproduct of the photosynthetic reaction is oxygen. The other, our stored fuel, in much of this work will be hydrogen. And so here again we will think about fuel cells as a very attractive means of replaying that stored energy. And what's nice about these reactions, of course, is that they evolve gases. And so we'll be simply responsible for collecting the hydrogen gas out of this cell and storing it or playing it back directly. But storing it for future use is one of the ways we can ensure that we have the desirable buffering characteristics that we're very interested in our energy storage lecture when we were discussing things previously. Another way to picture one of these artificial photosynthesis devices is that it's kind of a fuel cell turned around. Into a fuel cell, we input hydrogen, we evolve water, and there we generate electricity. And in one of these artificial photosynthesis devices, we take in our solar fuel, we take in photons coming from the sun, and we also input water, and then we split it and generate our storable fuel in the form of hydrogen. Now, the idea that we discussed in the context of photosynthesis of having an abundance of surface area, well, this is a theme, of course, that we've used throughout this course, and it will definitely come up here in the context of artificial photosynthesis. Here, the field of nanowires has been extremely important in making progress towards this vision of artificial photosynthesis. For again, they have these properties that we've now seen a number of times. They're capable of conveying in a directional fashion electricity, so their electrical conductivity is very good. They have an abundance of surface area. We can even put catalysts on the surface of these materials in order to ensure that our reactions move forward in the desired direction and with a high efficiency. And one of the leaders in this field is a really remarkable person whose name is Peidong Yang. He's at Lawrence Berkeley Labs. And actually, Peidong also manifests some of the qualities that make him such a successful nanotechnologist. One of those is that people going through their graduate training these days or doing their postdoctoral fellowships, becoming profs, they can go around to a number of different labs and collect knowledge, depth, methods of research from these different labs. So Peidong was in a group that was one of the leaders in the development of nanowires, and he personally, as a graduate student, led a lot of the most exciting work in the nanowire field for its own sake, even before they were being thought of for artificial photosynthesis. Then joined a group that was leading in the area of making these nanostructured materials for energy storage and catalysis and conversion. And so when he then went on his own and started his own Berkeley group as an assistant professor, he had this set of skills in engineering nanomaterials and thinking about their use in catalysis and energy and electrochemistry that very few other individuals around the world did. And it's this confluence of skills, how people are able to go accumulating a number of different sets of capabilities from different traditional disciplines that allows a lot of the innovations to occur within nanotechnology. Often it's not even so much a single brilliant idea, although that happens too. There's certainly breakthrough insights. But it's sometimes bringing up an individual who has a set of competences or capabilities that no other individual in the world has. And that's certainly the case in some of this work. Some of the most exciting stuff that's happened recently coming out of this group, the Berkeley group, has involved the use of nanocrystals as well as part of the catalytic process in order to pave the way towards artificial photosynthesis. One of the great things about nanoparticles is that they're not always just spherical like some of the ones that we've seen, these quantum dots. But instead, researchers are able to synthesize things like nanocubes. And here the facets that are available are different. So maybe when you picture a little cube of salt, you can picture the fact that potentially if you were to, instead of having it as be a cube, if you were to slice off one of the corners, you'd see a different atomic arrangement of sodium and chlorine atoms. Well, it's the same with these nanocubes that are used in the synthesis of artificial fuels, the artificial photosynthesis, that by controlling which facets are presented, we're able to achieve shape-controlled and also size-controlled metal oxides that have particular promise in achieving some of these interesting devices. In fact, one of the exciting recent discoveries that came out of Dr. Yang's group was the realization that one could put together a stack of materials where different layers within the stack carried out sequentially different reactions. So it's a bit analogous to in the photosynthetic reaction case where there's a cascade, there's a number of steps that each need to occur in sequence. They were able to first make a cerium oxide to platinum interface, so a first metal oxide to metal interface to catalyze a first reaction, which is to catalyze methanol to produce carbon monoxide and hydrogen. And then a second reaction was catalyzed at a second interface, but very nearby, a platinum to silica interface, where the first product of that first reaction was then used as an input to the second reaction. So it's this kind of cascade or sequence of reactions that we can engineer when we make multi-material stacks. And there's some techniques that are now extensively used in building up multi-material stacks. One of these techniques is called Langmuir-Blodgett assembly. And in this technique, people talk of using a Langmuir-Blodgett trough. And essentially one has a bath, a solution, filled with molecules. Often the molecules have a propensity to stick one way down on a particular surface and stick their tail up in the air. So they have a head and a tail, and the head has an affinity for a substrate or a surface that one will work on. And one can dip the substrate into this trough and gradually withdraw to the appropriate angle and the appropriate rate, and produce layers of molecules that are very, very consistent. In fact, one can even come along, use an atomic force microscope or other kinds of scanning tunneling microscopes, and one can even see these dense forests of individual molecules that pack themselves. It's a bit like crystals, but two-dimensional crystals, and not based on the traditional inorganic picture of crystals, but based on organic molecules that pack themselves into certain regions. Well, Peidong's group used the same technique, but now to deposit layers of nanocubes of platinum and cerium oxide on top of a silicon dioxide substrate. He made these nanocubes each on this scale of about 10 nanometers, and then made these two distinct interfaces that I spoke about. And these sequentially catalyzed the reactions. And so in the vertical dimension, he was able to build up a more complex stack, not just a single monolayer or a set of layers of the same thing, but a complex stack of materials. He called this a bilayer structure. And here, the analogy is a bit with those tandem solar cells that we spoke about in the context of solar energy harvesting. Then we were thinking of how to first harvest the visible photons, the energetic photons, as efficiently as possible, and subsequently harvest the infrared photons and achieve a total energy output from the solar cell that was the sum of the energies of these two inputs. Well, here the Berkeley group was able to stack these two reaction systems on top of each other and achieve this series process, a tandem cell for catalysis, as distinct from the tandem photon cells that we were talking about earlier. Carbon nanotubes have also played an important role in some of the progress that's been made in artificial photosynthesis. One of the key components of making these devices work is to achieve an oxygen-evolving anode, as it's called. So with oxygen being the product here, there's a lot of focus on making the electrodes that will lead to the production of oxygen, one of the outputs of these. In fact, this is really, part of the broader dream. It's to make the device where the catalytic splitting of water ultimately gives rise to this production of oxygen and to the production of the hydrogen fuel. Oxygen is the byproduct from the splitting of water. Hydrogen is the desired fuel that we're trying to generate. And researchers in Italy, collaborating with an Austrian group, were able to demonstrate that with the aid of multi-walled carbon nanotubes, really a conductive bed of these nanotubes, that they were able to make a particular style of oxygen-evolving anode. And it was also a multi-layered stack, but in this case, it wasn't just a planar device, but instead they were able to functionalize the surface of their carbon nanotubes, wrap a variety of organic molecules around them. And these organic molecules kind of had fingers that reached out from being along the tubes. They reached out into solution and were able to grab the constituents that were needed to participate in the reaction. So instead of building a sort of a sandwich up, a planar sandwich up vertically, they built an analog of that sandwich, but they built it out radially. And you can see that through this approach, there's obviously more surface area, more opportunity for interaction as well. Some of the images of the materials that they produce this way are really spectacular, and they showcase how much we can see now at the nano scale. We've seen lots of transmission electron micrographs throughout this course in which we looked at structure, where we looked at how even where the individual atoms were placed in quantum dots, we could see the crystallinity. But we haven't looked at too many so far in which people were actually looking at the elemental composition. So not just asking and answering the question, is there an atom present, but which atom is it? But using the best TEM techniques that we have available to ourselves now, we can do spectroscopy on the constituents, what we're looking at. So we can actually see, this is based on the electron orbitals that we discussed, the basis of the periodic table. Well, we can see spectral signatures in the loss of electrons as they propagate within these transmission electron micrograph systems. We can see spectral signatures through their energy loss of what is present. We can look for the atoms that should be abundant, but we can also look for those that are present at a low concentration. In the context of our semiconductor discussions, we call these dopants. They were available at very low concentrations, but they were used to influence the electronic properties of our semiconductors. They would donate an electron to the lattice, or they would create a semiconductor that was depleted in its density of electrons. Well, with these remarkable advances in microscopy, we're able to actually see the elemental constituents that build up, in this case, on the surface of these multi-walled carbon nanotubes. So the nanotubes themselves played a couple of different roles in this work on making these oxygen-producing anodes. One of them was they provided a basis for control over the material morphology. The researchers were able to control the surface, control the binding to that surface, and therefore build the structure that they desired. As we've seen many times now, it was a strategy that successfully increased the surface area, which gave them more opportunities per unit volume to achieve a particular reaction that was desired. And finally, through these tubes, through their conductive properties, they were able to funnel this sequential electron transfer to the electrode. So again, they were using kind of the orientation, the fact that they hadn't just made a nanoparticle that was essentially the same in all three dimensions, but instead a tube that was engineered to convey energy in a particular direction and to drive reactions in the perpendicular directions, in the radial directions, in that manner. Well, as you might have guessed with the analogy with biology, the inspiration from the photosynthetic reactions, from our desire to see whether we could make self-assembled materials or devices for water splitting, It's, of course, tempting to ask what Angela Belcher's been up to, because her work on engineering viruses that we discussed in the previous lecture for batteries, it seems logical that, especially if you're trying to build a system, or a system inspired by living organisms that can achieve these photosynthetic reactions but produce a different fuel, one such as hydrogen that might be preferable for many purposes, that the engineering of viruses towards this function might be attractive. And indeed, the Belcher group at MIT has worked on exactly that. And again, it's using these concept of biological templating, because that research group is so capable in engineering a library of viruses, and then identifying the few within that library that are inclined to stick to a particular surface. Say one that's particularly prone to achieving a desirable synthesis reaction, such as in order to achieve artificial photosynthesis, they were able to use the same set of techniques to engineer a virus scaffold that could allow them to assemble a virus that had two key components on it. So one of these was the photosensitizer, was the material that was responsible for absorbing the light and producing the excited electron, so converting the energy from the photonic domain, from the optical domain, from the sun, into the form of an excited electron ready to participate in a reaction. And they were also able to engineer their viruses such that they attracted a particular metal oxide, an iridium oxide cluster, that served as the catalyst. And so they were able to build these kind of integrated devices. And here again, the analogy is with the antennas that are so important in the photosynthetic reaction center. Here, the group was able to make these elongated viruses. From a shape and overall structural standpoint, they had something in common with the carbon nanotubes. They had this one-dimensional linear character. And here they were able to use the actual peptides or proteins that were displayed on the surfaces of these viruses to grow their nanoparticles, to put in place the porphyrins, so essentially the light-absorbing dyes that were required for initial energy harvesting from the sun, and then also to put in place the catalysts that they required. This discussion wraps up our conversation about the opportunities to use nanotechnology for efficient energy harvesting, and also for storage of that energy, and then also for its integrated harvesting and storage. We've touched on quite a number of themes. In fact, in a way, we've had the opportunity to integrate a whole bunch of the concepts that nanotechnology embodies. In fact, one of the broadest ones of those is simply that it's an intrinsically interdisciplinary science and technology. In order to, especially for this last lecture, in order to build an artificial photosynthesis system, one needs researchers, professors, graduate students who understand how photosynthesis works in the first place, so they have some biology, who understand the inner physics and chemistry of the reactions that occur then, who understand it so well that they can come up with new materials and new strategies that can implement these same broad concepts, but implement them in the case of hydrogen production. One needs materials scientists and materials engineers who have the capability to put together new material sets in very reproducible and reliable ways. One needs people who are capable in the analysis of these materials. These transmission electron micrographs, they're now available. Everybody can do it. I mean, every university has the capacity to take these images, but it takes a special person with the finesse and the delicacy to take these kinds of images. And so often you'll find that the efforts that go on in these fields now, they involve people who have the breadth to be able to think across disciplines, but they also involve quite big teams. These efforts are so ambitious. I mean, think of trying to create devices that mimic what trees and plants took millions and millions of years to figure out how to do. And they're trying to do something much more rapidly than that. Our energy challenges are urgent. We don't have millions of years. We maybe have a decade or two to come up with some new solutions on the energy front. And so these teams of very brilliant people are working together very collaboratively, very much across disciplines. And as the approaches taken get more interdisciplinary, these teams grow into quite large groups of people working very, very closely together. I think that energy represents one of the most important societal challenges that we have in front of us, but it also represents one of the most exciting opportunities to integrate some of the many, many concepts from across the science and across the technology of the nano world. We've spoken in the course so far about information and communications technologies and the role that nanotechnology has to play in advancing those. We've spoken of biology, biomolecules, and how nanobiosciences and nanobiotechnology have a real opportunity to play there as well. If you think about some of the big challenges facing the world today, another one that comes immediately to mind is the field of energy. How do we find ways to capture energy, store energy? How do we find ways to capture energy in a way that's renewable, that's sustainable, and that's clean? And so for the first lecture in this series on energy, we're going to talk about solar energy. In particular, how do we harness it? How do we turn it efficiently into electricity? And what role does nanotechnology have to play in that? First, let's spend a minute on the sun and its properties. We need to understand the sun and its spectrum in order to think about solar energy properly. First, on the spectrum, the sun is very, very hot, as you're well aware. And that accounts for the fact that the peak of its intensity, the peak of its emission, lies within the visible spectrum. We were speaking earlier about thermal imaging and how you can see a warm person against a colder background. Well, their wavelengths of emission are much, 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 much longer than the sun's. But it's all based on the same physics called black body emission. In the sun's case, because it's so hot, about 5,000 or 6,000 degrees centigrade, the sun peaks its luminescence, its intensity, right in the visible wavelength spectrum. And as we also discussed earlier, that's why our eyes have adapted to see in what we call the visible wavelengths. An important thing to know about the sun, though, is that in addition, it has a very significant spectral signature in the infrared, and not the very long wavelength, low energy infrared. There's a major portion of sun energy right up against the visible in what we call the near infrared wavelengths. In fact, fully half of the sun's energy lies in the infrared. And so a lot of the opportunity for making more efficient solar cells is going to be to make full use of the sun's broad spectrum. Another important thing to think about with the sun as we think about making a good solar cell is the breadth of that spectrum. It's kind of the opposite of a laser. In fact, if the sun were a laser, which it's not going to be, but if the sun were a laser, we'd have an easier time making solar cells because we could tailor our converters of light energy into electrical energy. We could tailor them to one specific wavelength. We could customize them. But inevitably, this is the source of energy that we have, and we have to make good use of all of its spectral components in order to make an efficient solar cell. So this will be one of our challenges, and I'll call it the broadband challenge. Instead of having a narrow spectrum, we have a broad range of colors, a broad set of bandwidths that we need to deal with. Let's start by asking kind of the economic question, though, the practical question on planet Earth. Far enough from the sun, is there actually enough energy to meet a significant portion of our energy needs? And if you were to look today at the way in which we meet our energy needs, and you look at fossil fuels and look at sources such as coal, look at nuclear, look at hydroelectric, and then you were to look at the proportion of energy that's met using solar energy, you'd find that a very, very small percent, much less than 1% of our total energy needs are met today using renewables. And you might then ask the question, well, is there some fundamental reason for that? Is there a lack of sufficient gift of solar energy reaching the planet Earth? And the answer to that is very much not. A couple of statistics there. One is, if you were to look at the total amount of energy reaching the Earth every hour from the sun, there's enough energy there to meet all of the world's energy needs for a year. Another way to look at this is if we were to cover the Earth with only a small fraction of the area of Nevada with good solar cells, not perfect, but just good solar cells, we could meet all the world's energy needs. So scaling by time or scaling by area, the same message is given, that the solar resource is abundant. And the reason why today we're not making fuller use of it relates to the fact that we haven't yet found ways to make solar cells that are simultaneously high in their efficiency and also low in their cost. And that's what we'll talk about much during this pair of lectures, is how nanotechnology is enabling us to seek to break compromises between cost and efficiency in solar cells. One more thing just to think about the sun before we move into the technology of solar cells is how it's distributed. Obviously, at the equator, there's both a little bit more intensity of sunlight, and then it's also better distributed throughout the year, and in some locations at the equator, we're also doing better in terms of cloud coverage. But the point I want to make with this map of insolation, which is the amount of energy per day or per year reaching different regions of the Earth, is that even if you live where I do in Canada, there's actually an abundance of solar energy. And if you were to compare us with the amount of solar energy reaching, say, right at the peak in Saudi Arabia, or right near the other locations right near the equator, it turns out that we have maybe 60% as much solar energy as they do at the peak. And given that there's this huge overabundance of available solar power, that's a lot. Even those of us who live well into the northern hemisphere have an abundance of solar energy available to us, and the challenge is to find the ways to harvest it efficiently and cost effectively. And so on that point about harvesting it cost effectively, this is where there's been some real advances through nanotechnology in recent years. Take a look at this picture of a physically flexible solar cell. You can see that it's bent. It's actually on a plastic substrate. And one of the great things about this new emerging area of solar cells that aren't rigid, they're not made on panes of glass, but instead they're printed onto flexible backings, is that we're able to make them a bit the way you'd print a newspaper. We're able to use roll-to-roll processing in order to make these flexible solar cells in a manner that's very cost-effective. Instead of being a sequential serial process like the semiconductor industry, we've talked about these semiconductor wafers that go through lithographic fabrication stepwise. Well, instead, it's a serial process, a continuous process. And these flexible solar cells are offering promise of significant cost reductions as a result of their ease of fabrication. The other great thing about being physically flexible is that their ease of deployment is enhanced as well. A significant part of the cost of getting a solar cell system installed isn't actually in the manufacturing the solar cell or the module that you put onto your roof. It's in putting it onto your roof. These heavy materials, sometimes there's a need to reinforce the roof as a consequence of trying to install these heavy materials on top of them. So lightweight, flexible solar cells that can be readily integrated into a building, in cases even integrated into the building materials themselves, offer great promise for reducing this other half of the cost of the solar system, which is often referred to as the balance of systems cost. Let's take a look at another slice at the kind of Moore's Law concept that we spent lots of time in on technological roadmaps. Silicon-based solar cells actually have their own Moore's Law as well, a rate of improvement in the efficiency to cost ratio in these solar cells. The challenge, though, is that if one projects this law, this empirical observation for the rate of improvement of power versus cost in these solar cells, one would predict that it would be many, many decades until we will have, based on conventional existing solar technologies, until we actually have these turn into compellingly cost-effective technologies. So this is where many in the field call for a breakthrough. They call for a need for something that will take us off the just extrapolative improvement in solar cell efficiency, and that will take us into a new regime. And so here, people talk about generations of solar cell. A first generation, such as the silicon solar cells that we will talk about together during this lecture, that have offered improvements in efficiency over time and reductions in cost, but not a disruptive change, not a step change. A second generation of solar cells that have been these flexible solar cells that have led to the emergence of the much lower cost approach, but where the efficiencies have not represented improvement over what silicon can give us. And then the vision, and this is much of the vision for the present work ongoing today, is for a third generation of solar cells, which doesn't have a compromise anymore, but which instead achieves lower cost and higher efficiency. And it's quite easy to see why this point about efficiency is so important. You might, until you think about these so-called balance of systems considerations, you might say, surely if I can just make my solar cells cheap enough, it's not particularly important that I harvest every photon from the sun efficiently. The photons from the sun are free. But when you then think about the fact that the cost of installing and maintaining solar cells, if you like, the cost of ownership and the cost of installation, these scale with the area of space that you're filling them into, then ultimately you need very much to think about efficiency. Because if you don't achieve reasonably high efficiencies from solar cells, you may be able to overcome the cost of the cells themselves, but you're not able to overcome these fixed costs associated with the installation and maintenance of the solar cells. And this is the reason why this third generation of solar cells is envisioned to be an area of very big opportunity for the energy sector. And so to be specific about the challenge that we're posing for the solar energy field, it's the following. It's that using existing technologies, which we'll dive into now, we've achieved certain efficiency improvements, but there are fundamental upper bounds, physical boundaries that we'll describe on how efficient you can ever get a solar cell based on a single semiconductor junction to be. And we're starting to get reasonably close to those bounds. And so with the incumbent technologies, there are limits to our capacity for further improvement. The opportunity for the third generation solar cells is to take us beyond those limits, is to make such better use of the sun's broad spectrum that we overcome the traditional limitations on solar cells based on a single semiconductor junction. So let's now dive in and let's talk about the basics of solar cells, how they work, how they relate to some of the materials that we've spoken about in the course together, and then ultimately how we're going to make them better using nanotechnology. So let's now talk about the semiconductors themselves. We've referred to semiconductors throughout the course. We've spoken of their different spectral absorption characteristics. We've spoken about how there are photon energies that are too small to be absorbed within a semiconductor, and others that are sufficiently energetic that they do get absorbed. Let's put a little bit more formalism or vocabulary around these ideas of absorption inside a semiconductor. And I'd actually like to start back at where we began. I'd like to start with atoms, the atoms that make up the semiconductor. When the elements, let's take a silicon element, silicon atom, for example, exist in isolation. They're not part of a semiconductor, but when an atom exists in isolation, it has these shells that we talked about, these shells that correspond to the energetic levels that electrons fill up that account for silicon's particular membership in a particular column of the periodic table. These are what we call discrete energy levels. They're very well defined. They're distinct. Only certain transitions, energetic transitions, are available, say, to a silicon atom. And in fact, those discrete transitions are much of the basis for how we're able to detect certain chemical elements. It's based on these very specific transitions, optical energetic transitions, that are available inside atoms. But in a semiconductor material, what matters is not just the behavior of the constituent atoms. What matters is what happens when they come together. And when these atoms come together, electrons, which as we know are delocalized, they have some extent, they start to merge and they start to participate in existing over many atoms. Now that, inside a semiconductor, is very advantageous. It accounts for the good electronic transport in semiconductors. The fact that, as we discussed earlier in the electronics context, these electrons can set up waves that have extent, that can propagate along a semiconductor. This is the basis for very good electronic transport inside semiconductors. What it also leads to is the establishment of what are called energy bands. So instead of having these discrete, defined steps, now there are ranges, entire ranges of energy where electrons are allowed to exist. They're allowed to propagate freely. And instead of having these original big chasms of energy in which no energetic states existed, now we have in between these bands what's called a band gap. And this too is a chasm, but it's not a chasm between just a pair of discrete states. It's a chasm between a band and another band. And so now there is a range of energies less than this energy gap or this band gap for which photons are not able to excite an electron from a lower band to an upper band. And in this case, there's no optical absorption. The material is transparent. In fact, even this concept exists in things we don't think of traditionally as semiconductors. So diamond, for example, also has a band gap. It just happens to have a very large band gap, which is why it's transparent to our eyes. Whereas if you were to look at a piece of silicon, to our eyes, it looks opaque. It's because it's absorbing all of the light across the visible wavelength spectrum. Its band gap lies out in the infrared. So you can see through silicon when you look in the infrared, but you can't if you look inside the visible. Well, how does this idea of band gap then relate to how we build a solar cell? Well, we need to match the band gap of our semiconductor to the spectral properties of the sun reaching the Earth, to the sun spectrum. And so certain semiconductors, such as silicon, have a band gap that's actually very well matched to the emission properties of the sun, or in particular the sun spectrum that reaches the Earth. In the case of silicon, it's actually just about the perfect choice. It was not something that we made a conscious choice to make silicon's band gap this way. This is a property of silicon atoms themselves. But it's a reason why we use silicon as a very appropriate semiconductor for making a device, for making a junction that's able to absorb the sun's light and turn it into electrical power. In fact, on that, it's worth pausing for just a moment and thinking about the relationship between the sensors, the light sensors that we spoke about earlier, and solar cells, for they have quite a bit in common. Each is responsible for absorbing light. Each, typically in the case of silicon, covers the visible and a little bit into the near-infrared wavelengths. But in the case of the sun, there's a preordained spectrum that we have to work with, and there's a preordained intensity. In fact, researchers working in the field don't even speak, usually when they speak of the sun, they don't even speak in terms of the absolute formal units. They talk about one sun. One sun is the unit of intensity to describe how bright the sun is. It's such a universal phenomenon that everybody having to deal with solar energy is conversant in. In the case of light sensors, typically the intensities that are being dealt with are much, much lower. And so they're both doing this optical to electronic conversion, but typically in different ranges of light intensity, many factors of 10 different light intensity. Now, the other thing is that in the case of sensors, we are converting information about the physical world into an electronic representation. And that means that if we need to apply a little bit of a voltage bias, we need to put a little bit of potential across our photodetector, that's perfectly fine, because we don't mind expending a little bit of power to run our sensor integrated circuit. But the name of the game in solar energy is in harvesting energy. And so when our goal is to harvest energy, we're looking for this device to take the sun's power, its photons, and to deliver them to us in the form of an electrical current, which can be driven across a load. So there's some voltage as well. And so the mode of operation of photovoltaic devices, of solar cells, is different as a result of that need to transfer power from the sun into some either system where we want to charge our car or to some means of storage, such as the case of a battery or a fuel cell, topics that I'll talk about a little bit later when we get to the field of storage. Let's dive in now and look at the heart of a solar cell a little bit. This is called a PN junction solar cell. And some of the details of the nomenclature aren't important, but what's key is to understand that when we build really any solar cell, we bring together two materials, typically having the same semiconductor properties, the same semiconductor band gap, but that are dissimilar in their affinity for electrons. So one of these materials will be rich in electrons. We will achieve that richness of electrons by introducing selectively a certain number of impurities that add electrons to the lattice, that donate electrons to participate in conduction. And on the other side of this junction, we will utilize a material that is depleted of electrons. And so now we have a structure which is electron rich on one side, electron poor of the other. And we've created the potential for a cascade. When we excite charge on one side of this junction, we now have a propensity for the electrons to want to go from one side to the other as a result of this built-in cascade, this built-in potential, as it's called. And that asymmetry is one of the crucial conceptual building blocks of any solar cell. The reason is that we're not going to be applying an external electrical bias. We don't get to have an applied potential on this device because we're trying to harvest energy. Instead, we've built a device that likes to absorb light and then funnel the energy that's extracted from that light in a specific direction towards a circuit. Now, the other point that we need to think about when we think about solar cells and their use of the spectrum and the limits on their efficiency is that, as we've discussed, because of this concept of a semiconductor band gap, there will be certain photon energies below which there's no absorption. So these colors of light simply pass through our solar cell. And there will be others that just barely cross the band gap, that just barely cross this chasm. These will lead to absorption. And in fact, this is a very efficient region of the spectrum for these solar cells because all of the energy in the photon that impinged upon the semiconductor is utilized ideally, is extracted from this. However, a sun spectrum is broad, and there are photons at much shorter wavelengths corresponding to much higher energies where there's an overabundance of energy in each photon. Now, if we could take that entire photon energy and harvest it, we'd be in great shape. But the way semiconductors work is that if you excite an electron well into a band, then extremely rapidly it trickles down right to the band edge. We say that these states that arise from silicon atoms coming together and forming these bands, we say that these states within a given band are very well coupled to each other. And so very rapidly, at room temperature, we get a loss of energy, and it's just converted into thermal energy, not something that we harvest inside a photovoltaic device. Now, this idea of loss within a band, loss of energy from a given photon, is very important in understanding the limits on solar cell efficiency. Because you might say from this loss consideration, well, okay, let's go find a semiconductor having a larger band gap. They're available. Then we won't throw away as much energy. We'll be able to deliver more voltage to our device. Ultimately, we'll be able to extract more power. However, if we were to do that, we would also absorb fewer photons because we would have made a larger band gap, and there would be more photons in the sun spectrum that were not able to breach that band gap. So this leads essentially to a trade-off. It leads to our choosing a semiconductor band gap that is small enough that we harvest many of the sun's, a good fraction of the sun's photons, but large enough that we don't do too much throwing away of energy from the juiciest, from the most energetic of these photons that come in. But it is a trade-off. And as a result, when one works with a semiconductor device, a photovoltaic device that is based on a single band gap, a single type of semiconductor, one is limited not to 100 or 97 or 95% overall power conversion efficiency, but instead the upper bound on the efficiency with which one can extract energy from one sun intensity, from the amount of intensity reaching the Earth's surface, is closer to 30%. It turns out that at the right price, that's not a bad efficiency either. But it's important to think about the limitations of solar cells based on a single choice of semiconductor and how they arise from making this choice to work with a material that has a fixed band gap and that leads to some loss of energy through this thermalization process within the bands. The final introductory concept that I'd like to spend a moment on with respect to solar cells is how do we think about this efficiency in terms of a current delivered and in terms of a voltage. Well, it turns out that the power, the electrical power that can be delivered, say, to your car for charging, or to a fuel cell or to a battery, the power of this is given by the product, multiplied together, the product of the current and the voltage. And so it's very important in solar cells to get as much current as possible and to get as much voltage as possible. And it's really managing this trade between those two through the choice of band gap that leads to the optimal band gap device and leads to the best management of this trade-off. So I'd now like to start in and talk about some nano concepts that allow us to make solar cells more efficient. And the first one of these I'd like to talk about relates to the management of light, to the management of photons. In fact, these concepts are already being utilized in solar cells that can be purchased today that are available. And one of these concepts it's actually quite simple to think about in terms of fabrication. It involves trying to make a rough surface, trying to make a textured solar cell. And the reason for doing this is the following. Within silicon, and we talked about this in the context of photodetectors, silicon is a reasonably good absorber. It's actually a very good absorber of blue photons, of the more energetic visible photons. But it gets much weaker in its absorption of light as we go to longer wavelengths, even those above its band gap. The name for this phenomenon is that silicon's an indirect band gap semiconductor. Now, when we try to make an efficient solar cell, clearly we're trying to absorb all of the light across the sun spectral region that we are absorbing at all, anything that's above the band gap. And it turns out to be necessary in silicon in particular to make a very thick wafer, a thick wafer of semiconductor in order to absorb all of the light in the infrared because of this weak optical absorption that occurs in the infrared wavelengths. And that is one of the things that's driven up the cost of silicon solar cells historically, is the need for a very thick quantity of very, very pure, very, very high temperature fabricated material. And what happens when we roughen the surface of a silicon solar cell is that instead of light simply passing into the cell and then, if it sees a mirror, bouncing back out, we instead create the opportunity for multiple passes through this device. So light is able to pass in, and then it sees this roughened surface. If you like, it sees a rough mirror. And instead of turning right back around and bouncing back out of our solar cell and losing its chance for absorption, it's typically reflected or scattered off in a different direction. And so instead of just leveraging the thickness of the device for absorption, if we can couple in and then couple sideways, we're able to increase the interaction length. We're able to overcome this weakness in the rate of absorption that occurs within silicon by using a textured substrate. It turns out that the exact shape that you want to do this with is actually very important. You want to think about the angles and even the sharpness of the angles that are used for scattering of light. In fact, this phenomenon where we get light into one of these semiconductor materials and then we get it trapped in there and we give it multiple opportunities to bounce around, it's called exactly that. It's called light trapping. And many interesting techniques have been devised in order to achieve this. Of course, if you had to make these spiky structures, every one exactly perfectly the same as all the others, that would be a challenging and probably a costly semiconductor patterning and etching process. It would start to look like what we do in microelectronics and nanoelectronics. But for solar cells, we're trying to make things that are big. We're trying to make things that can be spread across a roof and do so in low cost. And fortunately, a number of techniques have been discovered to make structured silicon surfaces without having to go in and actively pattern every little spike, every little valley in order to make one of these light trapping structures. And the technique actually uses a chemical etching where silicon has these particular directions. Like all crystals, silicon has these particular directions known as facets. These are like the facets of a diamond that you can see. And when you introduce a chemical etchant, they can chemically etch in a particular direction. They can etch along a particular facet. And so they're naturally prone to taking a planar surface and starting to carve it into these triangles, into these hills and valleys, or spiky mountaintops and valleys. And as a result, there are now very low-cost and convenient methods to make nanostructured silicon surfaces that are very prone to want to trap light. So we've covered the basics of solar cells. We've covered the huge opportunity that solar energy harvesting represents. We've talked about the underlying principles of matching the behavior of a semiconductor used to capture light with the broad solar spectrum. And we've just started to touch in on how nanotechnology can be our friend in enabling the efficient capture of energy from the sun. In our next lecture, we're going to dive in further and really spend time on how we're able to take advantage of the nano world, control over the coupling of photons to electrons inside semiconductors to make solar cells that break the historic compromise between cost and performance.
Throughout this course, we've looked at many different kinds of nanomaterials. And all of the materials we looked at were man-made materials. This could lead you to think of nanotechnology as something that humans invented. Well, that's not the case. And nature is even better at making nanomaterials than we are. What we'll find out is that nature can make nanomachines that are far more advanced than those that have been generated artificially. In this lecture, we'll look at a series of natural nanomaterials and nanomachines, and I think this will really give you an appreciation for the role of nanotechnology in nature. But so you're calibrated, let's start by looking at a few examples of nanomachines that humans have created. We've not yet talked about nanomachines, and this may have been something that you thought would actually take up much of the course. If you are familiar with Michael Crichton's book, Prey, you may be especially curious to hear about nanoscale robots, a type of nanomachine he describes in that book. The nanobots in that book are pretty nasty, and they're intent on taking over the world. Now, you haven't seen anything remotely similar to this, and that's because no one has ever made a nanorobot. This is a long way off and perhaps even impossible. So let's begin with a look at some nanoscale machines that humans have created and consider their abilities and limitations. Before we do, let's stop and think for a minute about what machines in general actually do. They typically convert one kind of energy into another. For example, many machines convert electrical or chemical energy into another type of energy or force. Movement is one way that this conversion is manifested. And then we have to be clever about what to do with the movement. For a car, it's pretty straightforward. We convert chemical energy, a force that propels the car forward by causing an axle to turn and with the two wheels attached. In a sewing machine, a needle moves up and down in response to consuming electrical energy. So in order to call something a machine, there really needs to be some kind of movement. Let's look at a pretty simple example of a nanomachine. This is a nanoscale motor that is made from a collection of fancy organic molecules. It has different domains that link two ends, and there's a chain in between. And then there's actually a ring threaded onto the structure. When an electron is removed from the complex, this changes the charge on part of the change, and in response, the ring moves from one site to another. So this is the idea behind making a simple nanomachine. We can use an external stimulus to create motion that could hopefully be harnessed to do some kind of useful work. Another very neat example of a nanomachine is the nano dragster. This was built at Rice University and uses carbon fullerenes as wheels. If we zoom in on the molecular structure, we can see that it has two large fullerenes at the back and then two smaller ones at the front. So the overall structure is actually like a nano dragster. The researchers who built this were able to get it to zoom around on a flat substrate, but in order to get the dragster to move, they had to heat it up to about 200 degrees. So this nanomachine is functional, but it uses lots of energy, kind of like a real dragster. And using thermal energy as fuel is not very practical. And there haven't yet been any breakthroughs that allow the nano dragster to power itself like a real car with chemical fuel, but there's lots of effort that is being invested in reaching this goal. Now, here's an example of a nanomachine that can use chemical energy. It's a nanorod that is half platinum and half silver. If you give this nanorod a solution of peroxide, it zooms around like a rocket. What's happening is that the gold portion is reacting with the peroxide to generate oxygen. The presence of the oxygen then helps the rod to zoom around. They are pretty fast, so the first nanorods that were engineered to do this could travel a distance 10 times their length in under a minute. A next generation version that contains more efficient catalysts travels 100 lengths in a second. The first model of this type that was generated had completely random movement, but eventually ways to control its movement were developed. A magnetic field could be used to orient the rods and get them going in one direction. Using a concentration gradient of fuel was also an effective way to control the movement of these nanorods. The gradient was produced by making a solution with different levels of fuel in different spots of a tank. The nanorods would then orient themselves to travel up a concentration gradient of fuel, and eventually they would congregate at the source of the fuel. Eventually, the same system was shown to be able to carry small cargoes around. A switching mechanism was even built in so that they could drop off the cargo at a defined location. Another application of the nanorods involves using them for sensing. Because they speed up in the presence of certain chemicals, tracking their velocity can tell you how much of a certain substance is around. This idea was recently used to detect cancer cells. A group at the University of California in San Diego attached an antibody to the surface of the nanorod, and then they showed that the nanorod could pick up a cancer cell selectively and then carry it through solution. By watching how quickly the rod moved, they could determine whether or not cancer cells were present in a sample. Now, I could give you many more examples of early-stage nanomachines with limited functionality, but I think by now you get the picture. We are a long way off from Michael Crichton's nanorobots. What he described were nanoscale creatures that could self-replicate by injecting themselves into bacteria. Not only is this a work of fiction that shouldn't be taken too literally, there are specific reasons why what Crichton envisioned could never come to pass. Many things, including friction, scale up when you miniaturize things. This means that a tiny robot would experience much more viscous drag, and flying through the air would be more like swimming through molasses. So these nanorobots could not keep up with a human in a chase, and they would be lucky to move even 1/10 of an inch per second, making it difficult for them to even keep up with a snail. So there are obviously technical challenges with making a robot move as Crichton envisioned. As well, other properties that he gave his fictional nanomachines, like self-replication, are also extremely remote or perhaps impossible. At present, I think most people in the nanotechnology field believe that this is not necessarily where we should invest our efforts, given that we have so many important problems to solve in medicine, energy, and computing. A more realistic concern than dangerous self-replicating nanorobots are questions about which nanomaterials at what levels might become harmful to humans or to other features of the environment. For example, silver nanoparticles that kill harmful bacteria might possibly get released into the environment and kill beneficial bacteria, such as those that are used in wastewater treatment plants. Some of the metals used in nanoparticles, like cadmium, are known to be toxic, and the unfamiliar properties of some materials at the nanoscale may possibly include new forms of nano-based toxicity. Now, concerns like this are reasonable, and there are many studies that show that we need to be cautious when we scale up the manufacturing of nanomaterials, and we need to think about downstream consequences. We also need to ensure that people who work with large quantities of nanomaterials take appropriate measures to avoid inhalation or ingestion. But it is also easy to get carried away with these concerns and contemplate throwing out the baby with the bathwater. But given what I hope you've learned about the promise of the materials we've described in this course, makes that seem like something that should really be avoided. Moreover, natural nanomaterials are actually everywhere in our environment, so they're not inherently dangerous. And I think this is an important point to consider when confronting claims about the danger of nanomaterials. So let's take a look at one of the most abundant natural nanomaterials. Diatoms are a type of tiny unicellular algae that are basically everywhere. They're in fresh water, they're in seawater, they're in our soil, and even ice. They are an important part of the environment, and they handle almost half of the recycling of carbon dioxide into organic molecules. Diatoms are also an important part of the food chain, and many fish rely on them as their main food source. And they've been around for a long time, so the first fossils of diatoms date from the Jurassic period 180 million years ago. Diatoms have a fascinating structural feature, and this is why we're talking about them. They have a coat made of silica with really intricate detail. Diatoms are really the ultimate nanoengineers. They put all kinds of nanoscale features onto their shells, and these are really amazing to look at. These things come in all shapes and sizes. There are over 16,000 different species. Some of the diatoms are circular, while others are square. Here you're looking at a diatom that's actually shaped like a peanut. Diatoms very often have shells that actually have multiple layers or parts, and this one has an extra covering around its middle. These structures can be as small as 1,000 nanometers across, but what is really amazing is the detail in the diatom shell. These organisms are somehow able to make nanoscale patterns in their shells. Now, how do they do it? Well, they take in silicon from the environment in a soluble form, and then once it's inside their cells, the diatoms put silicon into tiny vesicles. Vesicles are like really small soap bubbles, and some diatoms know how to make them shaped like rods or even donuts with holes in the middle. So they put silicon into the vesicle, and then the presence of some other molecules that are around causes the silicon to form a nanoparticle, or a nanorod, or a nanodonut, depending on the shape of the vesicle. The diatom then transports the nanoshape onto its surface, and particle by particle it grows a shell. Very intricate patterns get built on the surface of the diatom. We're not exactly sure how they template the pattern, but now that the genomes of several diatoms are sequenced, we have an idea of what proteins they have in their cells, and we'll probably be able to figure this all out. We also don't know what the function of the patterns are, but it's really amazing that nature can do this kind of nanoengineering, and there is undoubtedly more to learn. Another very interesting aspect of these organisms is how diatoms reproduce. They have to have some way of getting out of their shell if they're going to have any chance of reproducing. And we know that given their abundance, that they must be really good at replicating. It turns out that their shell actually has two parts that fit together, kind of like a petri dish. Sometimes there's a strip wound around the middle. We saw an example of one of these a few minutes ago, and this strip can help hold the two pieces together. Now, keep in mind that diatoms are just single cells, so they divide in order to reproduce. The two cells end up getting made inside of the silicon capsules, and then as they grow, they push the two parts of the shell apart. Eventually, the parts of the shell separate, and then each diatom grows the part of the shell that is missing. And I think it's very neat that they can reproduce this over and over again. So nanotechnology researchers are inspired by how good diatoms are at making nanomaterials. And they're also dreaming up new ways to use diatoms for different applications. For example, a group of researchers in Oregon figured out how to substitute titanium for the silicon in diatoms. They grew diatoms in the lab in reactors that contained a soluble form of titanium. And when they were done, they were able to determine that the diatoms were about 2% titanium. Now, this may not seem like much, but it should be enough to give these diatoms special properties. Titanium dioxide, unlike silicon dioxide, can be used for hydrogen production or solar energy conversion. So by manipulating the composition of the diatom shells, we may be able to use them to produce energy in new ways. There are also organisms in nature that are very good at producing a different type of nanomaterial, magnetic nanoparticles. There are certain types of bacteria that make these particles and keep them within their cells. It's not completely clear what the bacteria use the magnets for, but it does mean that they always stay aligned with the magnetic fields that surround the Earth. You're looking at a picture of a bacterium called magnetospirillum, and you can see that it has a chain of tiny particles running along its side. The presence of these magnetic particles was discovered relatively recently. It was 1975 when the bacterium and its particles were discovered in shallow pond water. The scientists that were studying them observed that when they took a solution of bacteria out of a pond and they put it on a microscope slide, the bacteria would all line up on one side of the slide. And they originally thought that the bacteria were navigating towards light. Bacteria sometimes do this to stay close to the surface of water because the oxygen concentrations are usually higher there. But the scientists eventually realized that they were responding to a magnetic field, a really interesting property, an unprecedented property for a bacterium to have. Birds have a more obvious use for magnetic particles. You may have heard about this. Birds can use internal magnets to help them navigate when they're migrating. The Earth has a defined magnetic field that varies in strength according to where on Earth a bird is. So then the magnetic particles that they carry can give them navigational information. So let's take a closer look at these particles and how they get made. The magnetic particles that are found in birds, and also the bacteria we just talked about, are made of a material composed of iron and oxygen. It's called magnetite, and it's very common. Magnetite has a metallic black color, and it's found in a crystalline form. We think that in nature, the magnetite particles get made in the same way as the silicon nanoparticles we just talked about. The iron is processed inside of a vesicle, and then a particle is formed. The locations of these particles have been studied in great depth in homing pigeons, who are obviously really good at finding specific locations. These pigeons have a set of 3 neurons that have magnetite particles within them. Now, we actually don't know how birds transduce the information coming from these particles, but we do know that the magnetic particles help them figure out whether they're pointing north or south. We think that birds use this information not only to make sure that they're pointed in the right direction, but also to know where to stop for food. A study done a few years ago showed that nightingales that were exposed to the same magnetic field as they would experience in northern Egypt would eat more and really try to bulk up a bit. Northern Egypt, it turns out, is an important stopping point for these birds. And it's one of the last places that they can stop before they have to cross the Saharan desert. Birds are really smart about not loading themselves down with too much body fat, but to make it across this desert, they usually need to gain about 3 grams of fat. This is the same amount they gained when they were exposed to this magnetic field. So there seems to be a strong link here. Some kind of signal is being transmitted to the neurons that are in contact with these nanoparticles. It's really amazing that these nightingales and other birds have evolved to use nanomaterials as a homing system. Now let's look at one last example of a natural nanomaterial. We've all marveled at the beautiful colors in butterfly wings and the intricacy of the patterns that different butterflies have. Beyond being nice to look at, these patterns are actually really important for the mating of butterflies and the ways that they recognize one another. And it turns out that what determines the shape of the pattern and the actual colors that show up on butterfly wings is the nanostructuring of their wing scales. If we zoom in on the wing of this butterfly, and this is a butterfly called a juniper hairstreak, we see a very complex pattern. And there are structures there. If we really zoom in with fine resolution, we can see structures that are about 2,000 nanometers. But you can see that there are even finer nanostructures underneath them that are about 100 nanometers. And this is what actually produces the light green color on the butterfly's wings. Small changes in the spacing or the shape of the pattern will cause the wing to reflect a different color. So this type of nanopatterning, which can be controlled very finely, is used to create very intricate designs on butterfly wings. You've probably also seen iridescent beetles and other brightly colored bugs. Now, what's behind the actual colors that we see? Colors can come from a variety of different effects. So they can be the result of interference, like when we see colors on the surface of a soap bubble, that's coming from interference. Or color can come from diffraction. This is something that happens when a beam of light interacts with features that are really the same size as the light waves. Color can also be the result of scattering. The very blue color that we see on a blue jay results from scattering rather than the presence of actual pigments. Similarly, the color that we see on most butterfly wings comes from thin film interference, where the coloration is due to alternating layers of high and low refractive index materials. So in short, the patterns that are used to generate the interference and produce colors that we can see, all of these colors really originate at the nanoscale. So these are a few examples of nanomaterials made by living organisms that seem to be very safe and compatible with sustaining life. Now, let's turn back to the idea of machines at the nanoscale, and let's look at what kinds of machines nature has developed. Scientists are really just endlessly impressed and inspired by the intricate variety of molecular machines that nature has created. Also, nature is really good at making very efficient machines. All of the energy produced in our bodies is produced by a nanoscale machine called ATP synthase. This machine uses hydrogen atoms as fuel, and it produces a molecule called ATP, which is essential for almost all of our body's functions. ATP synthase has many different components. It's quite a complex nanomachine. But the most important component is a rotating stalk that sits in the membranes of our cells. When a hydrogen atom comes along and is taken into ATP synthase, this causes the stalk to twirl, and the protein then uses the energy created by the movement of the stalk to make a molecule of ATP. This is an incredibly efficient machine. Every hydrogen produces one molecule of ATP, and the synthase never misses. There are also nanomachines within our body that produce all of the proteins our cells need. This machinery is called the ribosome, and it's a complex of 3 very long RNA molecules and about 75 different proteins. It measures about 30 nanometers, and there are many, many copies of the ribosome throughout our cells. This image shows ribosomes lined up on a long strand of RNA. And what they're doing is they're reading the sequence of RNA and they're converting it into a protein sequence. This is a really amazing machine. It does this all by consuming chemical energy. A very complex set of steps is carried out by the ribosome. It first binds what's called a messenger RNA. This is a piece of RNA that is, you can think of it as a transient copy of a sequence found in the DNA genome. It's just converted into RNA. Then the ribosome recruits what are called transfer RNAs. The transfer RNAs are what match up with the sequence of the messenger RNA, and each transfer RNA has an amino acid attached. So in response to the sequence of the messenger RNA, the transfer RNAs line up, and then the ribosome zips together all the amino acids to form a protein. The function of the ribosome, a tiny nanomachine, is highly programmed and really specific. The ribosome very rarely makes a mistake, and it can't afford to, given how important our proteins are to the functions of our cells. Another very impressive natural nanomachine is made possible by a substance called actin. Actin is a protein that polymerizes and can form extended structures. This image shows the actin filaments in a cell lit up with a dye. You can see that it forms a really complex network across the cell. Actin forms a nanomachine with another protein, myosin. And this complex between actin and myosin gives our muscles the ability to move around. Myosin harvests energy from ATP to propel itself along actin filaments. This is how we get movement at the nanoscale. And this movement is translated to movement in the real world at the macroscale because our muscles have fibers in them that have lots of actin and myosin. So billions of myosin molecules consuming billions of ATP molecules is the basis for how we get around. And it's all because of the nanomachines that can get the work done. And this is a really good example of the collective impact of lots of nanomachines. We have to keep in mind that the size scale of nanomachines makes it such that for their work to be manifested in the macroscopic world, we'll probably need to put billions or trillions of them to work at once. So have we been able to reproduce artificially the functions of the kinds of natural nanomachines we've just spoken about? Not even close, unfortunately. As you've seen, we've really only been able to make machines that can move around in pretty simplistic ways. We've not yet come very close to making a machine that could actually make a product, chemical or otherwise, like the ones that natural nanomachines make all the time. On the other hand, our ability to understand and use the astonishing nanomachines provided by nature is getting better and better. The development of all the tools that nanotechnology researchers have at their disposal allows us to take a look at biology at a very detailed level and learn from it. It may be that our best bet when it comes to making nanomachines is to take what nature has come up with and figure out how to control it using the tools of nanotechnology. This is an approach that is currently being pursued to generate what are called biohybrid devices. These devices might be able to harness, for example, the contractile movement that actin and myosin can produce and control individual muscle fibers to get more controlled movement at the nanoscale than we've seen so far. I think this is a hugely promising approach that has a lot to contribute, and it may well move ahead faster than our trying to replicate or replace what nature does from scratch. This lecture is the last that will discuss the biological aspects of nanotechnology. Now, in the concluding lecture, Ted Sargent will describe another set of very exciting discoveries and developments on the horizon. I hope you now have a better appreciation for what a good nanoengineer nature is. a perspective that really ties together nicely with the previous material we covered on nanomedicine. Here we've seen that biology is really good at nanoscale engineering because all of its building blocks are nanoscale. This is the very same reason that nanotechnology is so important for medicine. In medicine, it's essential to be able to get down to the nanoscale in order to make drugs more effective, surgery more precise, and disease diagnosis more sensitive. We also know that if we want to convince cells to form tissues, we need to give them the same nanoscale clues that they get within the body. So I hope that this material has given you a clear picture of the promise of nanotechnology for important medical advances, and the central role of nanomachines in nature, and how the nanoscience of nature and medicine are related, and will become even more interrelated in the future. And most of all, I hope you found these areas of nanotechnology as fascinating as I do.